Welcome back, chemists. Today we're going to be talking about specific heat capacity and how to measure heating and cooling. But first I want to review a little bit of what we talked about last week. We started with talking about the difference between heat and temperature. Remember, temperature is looking at how fast particles are moving, and it's going to be measured in something like Celsius, Fahrenheit, or Kelvin in degrees, where heat is looking at both the speed and quantity of particles. And total energy there, and that's going to be measured in joules. All right, you looked at heating and cooling curves, and hopefully we're able to analyze and answer questions about those. And we also talked about phase changes and how to calculate heat involved in those. Remember, heat's always going to be in joules, mass is going to be in grams or kilograms, and the heat of vaporization and fusion are given to you on your reference sheet. So today we're going to talk about heating and cooling some more, but when things aren't changing phases, but changing temperature. Okay, so when a substance is heated, that means energy is being added to it, so the particles move more and the temperature is going to go up. Whereas if a substance is cooled, heat's being released, which slows the particles down, causing the temperature to drop. In order to calculate it, we use this formula here, where again we know delta H is heat, which is going to be in joules. M is mass in grams. C is something new. This is called specific heat capacity. And if you look at the definition down here, the specific heat capacity of a substance is the energy required to increase the temperature of 1 gram of a substance 1 degree Celsius. So kind of a mouthful, but it's something like density. Every substance has their own unique specific heat, and you can find that on your reference sheet. And then the last thing is change in temperature. Notice that triangle, again, it means change, because we're looking when something's getting hotter or colder. So it's final minus initial. Okay, and that's going to be in Celsius. So when you're solving these, you don't need to memorize all the different specific heats, because if you look, they're given here. So use your reference sheet. You have it on our Google Classroom. I suggest printing it out if you don't already have one in your notebook, because it's good to reference there. You have your formula here, and then all specific heats for different common substances there. So let's do a couple practice problems. So here's practice problem 1. It says calculate the amount of heat required to heat 100 grams of water from 30 to 40 degrees Celsius. How many kilojoules is this? So in this case, we're looking for heat, or delta H. So let's look at what we're giving. 100 grams would be our mass. And it says water, so if I look at my reference sheet, the specific heat of water is 4.18 joules per gram degree Celsius. Remember, specific heat's a ratio. And then we have two temperatures. Remember, change in temperature is final temperature minus initial. So our final is 40 degrees and our initial was 30. So to get our delta T, it would be 40 minus 30, which is just 10 degrees Celsius. So now that I have all of my givens, I can go ahead and plug into the equation. So to get my delta H, remember it's MC delta T, so my mass was 100 grams. My C is listed for water, which again, you don't have to memorize, it's on your reference sheet, is 4.18 joules over grams times degrees Celsius. And my temperature, sorry, that's times, is 10 degrees Celsius. Notice my units. The Celsius will cancel, the grams will cancel, and I'm left with joules, which is good because I'm looking for delta H. And if I plug that in my calculator, I should get delta H equals 4,180 joules. Now, this is good, but remember the problem asked for kilojoules. So a little blast from the past, first semester. Remember, kilo means 1,000, so in this case, I'd move my decimal over 1, 2, 3 places. So my answer would be 4.18 or 4.180 kilojoules. So this one was a basic delta H problem. If that was challenging, I might go back through the slides and try again on your own before moving on, because now we're going to look at looking at the other variables. So if you look at problem 2, it says calculate the mass. So we're going to look for something different this time, of gold that requires 208 joules of heat to heat from 30 to 80 degrees Celsius. Now, I want mass. So to get mass alone, what I'm going to do is I'm going to divide both sides of the equation by C delta T. Okay, so my new formula I'm going to use will be mass equals delta H over C delta T. Okay, now notice this said gold, so before I do anything, I want to look at my reference sheet for the specific heat of gold. And if you look there, it is 0.130 joules over grams degrees Celsius. Okay, so I have my specific heat capacity. If you notice, you were given delta H right here. And then I have my final and initial temperature. So again, to get my delta T, I'm just going to subtract my final from initial. So in that case, for delta T, I have 80 degrees minus 30 degrees, which equals 50 degrees Celsius. So now I'm ready to go back and plug in for M. I'll change my color so it's easy to follow. So for mass, I have delta H, which is 208 joules, and I'm going to divide that by my specific heat capacity, joules over grams times degrees Celsius, times my change in temperature, which was 50 degrees Celsius. And again, if I look at my units, temperature cancels, the joules cancels, and I'm left with grams, which is good because I want mass. And if I plug that in my calculator, I will get 32 grams of gold. So I've showed you how to calculate for heat and mass. Now we're going to keep going and try for some other things. So in this problem, it says calculate the change in temperature, so delta T, if 2100 joules of energy are used to eat 250 grams of glass at 150 degrees Celsius. What is the final temperature of the glass? So let's look at what we're given. So 2100 joules of energy, that's going to be my delta H, are used to heat 250 grams, that's my mass, of glass. So let's look at our reference sheet for the specific heat of glass, and you'll find that it is 0.840 joules over grams degrees Celsius. And then it says, what is the final temperature? So notice we're given this temperature right here, 150 degrees Celsius. That's the initial temperature. So I'm just going to ignore that right now because the first thing I want to do is figure out the change. Okay? So looking at my equation to get the delta T by itself, I'm going to go ahead and divide both sides by MC. So my new equation will be delta T equals delta H over M times C. Okay, so I'll go ahead and plug in what I have. So my delta H, we said, was 2100 joules over my mass, which was 250 grams. And our specific heat, which again I found on my reference sheet, is 0.840 joules over grams degrees Celsius. I'll look at what units cancel out, joules cancel out, grams cancel out, and I'm left with degrees Celsius, which is good because I'm looking for change in temperature. And my change in temperature will equal 10 degrees Celsius. Okay? Now, that's part of the problem. That's the first part. But then remember, it also asks for us to calculate the final temperature. So remember, delta T is final minus initial temperature. And if you look, that 150 was the initial temperature. So what I'm going to do, I'm going to go ahead and add that to both sides to get TF by itself. So my final temperature is going to be delta T, which I just got, plus my initial temperature. So if I plug it in, I'll get my 10 degrees, which I just calculated, plus the 150 degrees we started at, which means my final temperature is going to be 160 degrees Celsius. So notice there are two parts to this problem. It's really important you're reading the whole problem to see what it's asking for. Because again, it asks us to calculate the change in temperature, but also the final temperature. And that's why I had two answers. So let's do one more. And in this one, it says calculate the specific heat capacity, which remember is C, of a substance if 780 joules of heat energy, that's going to be my delta H, raises the temperature of 50 grams of a substance, my mass, from 100 to 140 degrees Celsius, which I'll use to get my delta T. Identify the substance. So before I go ahead and try to solve this, I want to go ahead and figure out what my delta T is. I'll use those two temperatures. Remember, delta T is final minus initial temperature. So in this case, my final temperature was 140 and my initial temperature was 100. So my delta T is going to be 40 degrees Celsius. Okay, now remember this equation was asking for C. So to get C by itself, I'm going to divide M times delta T. Okay, so that we can cancel those both out on both sides. So my new equation will be the specific heat capacity is equal to delta H divided by M times delta T. And at this point, I have enough information to solve it. So I'll just go back and plug and chug. If you look above, we said that 780 was our delta H, so 780 joules. The mass we were given was 50 grams. And then we just calculated our delta T to be 40 degrees Celsius. So notice nothing cancels out this time, and that's actually good because remember, C is a ratio. So if we do our math, okay, you'll get that C is going to be equal to 0.390 joules over grams times degrees Celsius. The last part of the problem asks you to identify the substance. At this point, I would look at my reference sheet and I would see that this is equal to nothing else but copper. Okay, so that's how you solve specific heat problems. You look at what you're given and what you need to find, and you manipulate the equation. Okay, so just to recap at the end, when a substance is heated, that means energy is added, so its particles are going to move more and the temperature will rise. When a substance is cooled, energy is released, so the speed of the particles will decrease, the temperature is going to go down. To solve heating and cooling problems, you use the equation delta H equals mc delta T, where delta H stands for the total heat, M is mass, C is the specific heat capacity, which you can find on your reference sheet, and delta T is the final minus initial temperature. Remember, specific heat capacity is a unique quality for different substances, and it's the energy required to increase the temperature of 1 gram of a substance, 1 degree Celsius. So you're going to go ahead and do a couple check for understanding questions. If this was a little hard, I suggest going through it one more time before you try them. And yeah, that's it for today, chemists. Have a great day.